Okay. I'm not gonna mess with the camera. Let's get started. So, quick recap for some of the stuff we ended up talking about last week. Last week we started chapter 0 of the book, the introductory chapter. Largely what this chapter is going to do is introduce you to some general definitions that are pretty much used in every field of mathematics and some common notation that's used all the time. And so, first notation we talked about was common sets. Empty set, natural numbers. Natural numbers include 0, so 0, 1, 2, 3, etc. Z, the Z here is the integers. If I do Z with a plus sign up there, then that's all the positive integers, 1, 2, 3, 4, 5. If I do it with just a negative sign up there, then it's all the negative integers, negative 1, negative 2, negative 3, etc. And you'll never see both plus or minus up there. That's nonsense notation, how I have it written. It's one or the other. No, all the integers that are both positive and negative.
Oh, not including 0.
0 is not positive, 0 is not negative.
Right.
So that would be nonsense notation. You can't have, if you take all the integers that are both positive and negative, you took this set.
What? That's the empty set.
I know. There's no integers that are both positive and negative. Oh. Okay, and then this symbol, that was a symbol for the rational numbers, and then if we put a plus up there, we mean all the positive rationals. If we put a minus sign, and all the negative rationals. Using high-level language, what are the rationals? All the numbers that can be expressed as fractions of integers. Yeah, you can't do like square root of 2 over 2. That's not rational. And then finally, the reals, which are pretty much anything you think of when you think of a number. If we do the plus there, we mean all the positive real numbers. If we do the minus up there, all the negative real numbers. Okay. And then we love to abuse this notation here, our interval notation. So when I talk about the interval AB, what are we talking about? We are talking about all the numbers that are between A and B, all the real numbers between A and B. So this should be, should I put my colon there? I should say it's all the x in R such that A is less than X is less than B. That's what the open interval AB is. All the numbers between A and B, not including A, not including B. If you were to see it on a number line, if I were to say here's A and I were to say here's B, then it'd be all the numbers in between. And sometimes what we do is we put a circle there, and then we fill in the middle part, specify all those numbers. Now, if A happened to be 1 and B happened to be 17, it would be all the numbers between 1 and 17, not including 1, not including 17. Square root of 2 would be one of the numbers in there, right there. Not drawn to scale. Okay, so then we have this notation. If we replace the open brackets with closed brackets, then that's all the numbers between A and B, including A and including B. So this is a set of all x in R. It's a set of all real numbers that are greater than or equal to A and less than or equal to B. So same thing, we just replace the less than signs with less than or equals to. So we include the endpoints. Now this one, we can also mix and match this notation. We can include the A but not include the B. So this would be all the x in R such that x is less than or equal to A but still just less than B. Then we have notation like this. We can sometimes use infinities in the notation. When we use infinities in the notation like that, let's see, this is all the numbers between A and infinity, including A. What are all those numbers? Well, they have to be greater than or equal to A. So I know A is less than or equal to the x's that we're talking about. And what do the x's have to be less than? Infinity. So we put and less than infinity like this. No.
Okay, so
and this is nonsense. We don't really put that. We just say all the x greater than or equal to A. We don't say and less than infinity. Less than infinity, that's nonsense. Similarly, if we want to do negative infinity to B, not including B, this is all the x in R where x is less than B. And we don't say and x is greater than negative infinity. And then finally, if we say all the numbers from negative infinity to infinity, what are those numbers? That's all the numbers. That's another way of just saying this set, R. Right? Okay. Example. You see the open interval, 1 to 2. What are these numbers? It's a set of all x in R where 1 is less than x is less than 2. Example of something in there, square root of 2. Another thing in there, pi halves. Right? Okay, let's look at this one. Close bracket 1.976 to 1.976. It's just a set containing that single point. The set containing the one number, 1.976. The single element set. How many elements were in this set?
A lot.
An infinite amount. Not just a lot, infinite. And not even countably infinite. More than that. For those of you who have worked with infinities before. Okay, so there's some examples with this interval notation. We use it a lot. All right, next. Our first definition from the book, definition 0.1, 0 because that's the chapter we're in, the first definition in chapter 0. Let D be a set such that, let's remember how to read this notation, for all little d in big D, there exists a set, we'll call it S sub little d, and let C be the collection of all sets S sub D. So D is a set of elements, and C is a set of sets. C is a collection of S sub D's. So D is a set of things. C is a set of sets of things. We'll get to that a little bit more here. But so far, for every little d in big D, for everything in this set, there's a set in C. For every element in D, there's a corresponding set in C. So we're creating a correspondence between two sets. Then C is an index collection of sets, or a collection of sets indexed by D. We refer to D as the indexing set, and we denote C by the set of all S sub D's for each little d in big D. It's going to be dense notation for talking about these sets. You got to get used to it. Or we just write the set of all S sub D's where it's understood from context what big D is. All right, let's get a concrete example because this is dense. Until you get it, then it just feels like I'm repeating myself 100 times. Hopefully that doesn't rub against me. That would be annoying. Pointed up. Okay, so here's an example. We're going to use T as our D in this definition. T in our case is going to be the set of all little t's where T is a town in Arizona. So big T is a set of all towns in Arizona. Each little t is one town in Arizona. So Colorado City's in here. We're going to use town and city interchangeably. So Phoenix is in here. So Flagstaff is in here. Okay. And let B sub little t be the set of all B where B works as a barber in town T. So if we're talking about B sub, pick your town, B sub Colorado City, then that is going to be a set of all barbers who work in Colorado City. And if we had B sub Phoenix, that would be the set of all barbers who work in Phoenix. So we took some initial set, the set of all towns in Arizona, and for each town in Arizona, we created a corresponding set, all the barbers that work in that town. Take our set of all barbers and throw them together in a collection C. That's what C up here is. So D is acting like our set of towns. And for each little d in big D, a little d would be a particular town. In big D, there exists some set S of D. In our case, it's the set of barbers that work in that town. And then C was a collection of all those S of D's. So C was a set of all the sets of barbers for each town. So let T be the set of all little t where T is a town in Arizona. Let B sub T be the set of all B where B works as a barber in town little t. Then what would the set of all the B sub little t's for each little t in big T be? This would be the set of all sets, the internal sets would be the sets of barbers that work in. So this would be the set of, I don't know how to write them, but this would be all the barbers in Phoenix, comma, all the barbers, and I'd list them out, in Colorado City, comma, and we keep going for each town in Arizona.
This work allow different barbers to work.
Yeah, the same barber can work in different towns. This right here is just notation. Oftentimes we create a collection of sets where each set is associated with a particular object from another set. So we're creating sets of barbers where each set of barbers is associated with a particular town in some set. I have a set of towns, and now I want to create a collection of sets where each of the sets in there is the barbers that work in a particular town. So I start out with an initial set, and with each element in the initial set, I'm associating an entire set. With each town, I'm associating an entire set of barbers.
This is a way to add additional identifiers.
It's a way of relating sets to each other. So that we can get this notation. This notation is extremely useful.
Reminds me of the student and classroom students.
Kind of. Could have done a similar thing for that.
I want to revisit it. Solve that problem.
We could make D here the set of all classrooms, and then S sub D would be the set of all students in that particular classroom. So in that case, D here would be, if we just talk about this main building, 1, 2, 3, 4, 5, 6, 7, 8, and S sub 5 would have us in it. And S sub 6 right now is empty. So that's one example. Going back with our barber example, trying to get real concrete with some small sets here. So I got my set of towns, and we got Colorado City, Phoenix, and Flagstaff for towns in Arizona. There's a couple. And then we got the barbers in Colorado City. We'll say that there's Bob and Frank. And the barbers in Phoenix, we'll say that there's Jack, Bob, and Bill. The barbers in Flagstaff, we'll say that's Frank, Bill, and Dave. Then the set of barbers that work in town T for each little t and big T would be the set of all these sets. Notice that this is shorthand for this whole set. So that is that set. So it's a set of sets. Each of those is a set written out right here. So for each T up here, down here I have an associated set. With Colorado City, instead I have all the barbers that work in Colorado City.
Call that index collection.
This is the indexing set. This is an index collection of sets. And it's indexed by this set.
You would say that that set is index collection that's on T, or would you say it's, is that how you would say it?
This is an index collection of sets by T. It's indexed by T. T is how we're indexing it. Dense, but once you get it, you kind of get it. We have set B sub little t for each little t and big T.
So, to the abstract, there really have to be correlation between any of those sets for you to make the index set.
It's just how we're naming it. Notice that the way I'm naming these sets is by the names up here.
Right. How do you, so you just have to state that there's an association B sub Phoenix and
Yeah, it's just a naming.
how do you use
It's the same way that you do it easy. You make your indexing set numbers. You do this all the time. You say we want to look at sets A sub 0, A sub 1, A sub 2. You're indexing it by the set 0, 1, 2. That's what you're doing. And it's just understood from context that that's what you're doing. We're making this type of notation explicit if I want to say the set of all those. And then some student says, but what does A sub 0 have to do with the number 0? Well, nothing. I'm just naming it. It could have something to do with 0. Maybe it does, maybe it doesn't. The point is, it's just my way of indexing these sets. That's all we're doing. So I can index them by these numbers, or in this sense, the data makes more sense, how we're indexing it. Yeah, t could have just as easily been 0, 1, 2. And then this would be 0, 1, 2. Yeah, each little t and big T. Here's big T. Little t and big T, little t has to be that or that or that. So b sub little t.
Basically, it's like a way to work.
It's a way to index your sets. Yes. That's what it's for. Okay, special case, which we kind of already just went over. When d is consecutive positive integers, so before we had a d here of Colorado City, Phoenix, Flagstaff. So our indexing set was that. Special case, when d, our indexing set, when our indexing set is consecutive positive integers, or in other words, d starts at some integer n, then goes to n plus 1, then n plus 2, all the way up to some integer n. Consecutive integers is like 5, 6, 7, 8, 9. Those are consecutive integers. Starts with an integer and increments by 1 to some ending integer, from m to n. So if d is consecutive positive integers from m to n, then we may write s, instead of writing s sub d for each little d and big D, we may instead write it as s sub d, where d starts at m and ends at n.
Okay.
So up here, we have, let's go back to what we had when we switch this out to numbers. If I switch this out to numbers, 0, 1, 2, this is, and then this is now 0, 1, 2. We make them equal to these things. We say that these are the barbers in town 0, these are the barbers in town 1, these are the barbers in town 2. Then now, b sub t for each little t and big T is b sub 0, b sub 1, b sub 2. That's perfectly valid. Another way that we could write this now is we could say this is a set of all b sub t, where t starts at 0 and ends at 2.
So it doesn't necessarily have to be positive.
Consecutive integers, consecutive positive integers. We'll only do this with positive integers. You could define it with negatives, but we never do that. I won't say that. Yeah, it's going too far down the street. So you might see this type of notation. B sub t, where t starts at 0, and we keep incrementing by 1 until we get to the number up here, 2. So this and this are saying identical things, but only in the special case where this t is iterating over positive integers. In this case, it happened to be iterating over 0, 1, 2. And that's what this says. T starts at 0, keep iterating until we get to 2. So just notation. Again, remind you what this chapter is going to feel like. It's going to feel like I'm just regurgitating a bunch of notation on you. But then when we start topology proper, we're going to gradually reintroduce it as needed. The point of this first chapter is just to dump it all on you at least once before you see it again in context of topology. So it feels like a lot. That's how it's supposed to feel. Okay, so that's our special case. So let's do an example. One that I might want to do is collect all the students in the school based on their age. So all the possible ages for high school kids might be 14 to 20. I don't know. So they can be 14, 15, 16, 17, 18, 19, or 20. So we have consecutive positive integers here. So I let D be the set of what I think are possible ages for a high school kid to be. And then S sub D is going to be the set of all X, where X is a person that is D years old. So S of 14 is a set of all students that are 14 years old, etc. So then, writing out all those S sub Ds, one way we could do that is we're saying the set of all the students then would be the set of all the students who are age D, where D starts at 14 and keeps incrementing until it gets to 20. So this is how we would represent the collection of all the sets. This is the same thing as this. S of 14, comma, S of 15, comma, S of 16, comma, dot, 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 comma, S of 20. Just notation. All right. Okay. A collection of sets, S of D. So when we got one of these things, S of 14, 15, blah, blah, blah. Certainly ruined my 14. A collection of sets like this is said to be nested, provided that the previous set is always a subset of the next set. Why do I think that's backwards? Let me double check that. Oh yeah. What definition is this? Definition 0.2. S of D plus 1 is a subset of S of D. I did have it wrong. The next set is always a subset of the previous set. There we go. So imagine that we come back up here and we redefine this. Rather than x is d years old, we define this to be x is at least d years old. Now this would be, this set right here would be a nested set. Because if we look at everyone that's at least 14 years old, then the next set, everyone who's at least 15 years old, is a subset of that. Everyone who's at least 15 is at least 14. Everyone who's at least 16 is at least 15. Everyone who's at least 20 is at least 19. And so that would turn this collection into a nested collection. So a collection of sets, S of D, where D starts at M and goes to N. So it only makes sense when we can order it with these positive integer ordering. It only makes sense. This nested notation only makes sense when our indexing set is consecutive positive integers. Because notice we're using this notation. This notation only makes sense with positive integers, consecutive positive integers. So a collection of sets like that is nested, provided that the next set is always a subset of the previous set for all k from k equal to m, wherever we're starting, all the way to n minus 1. Why n minus 1? Well, when we plug n minus 1 right there, we get n, our last set. So let's look at another example of a nested set. Let S of n be, now this is the closed interval from negative 1 over n to 1 over n. Then S of n for every positive integer n is a nested set. So what is S of n? Let's write out this set. Get a feel for this. So S sub n for each n in the positive integers. This is going to be equal to the set of, what's the first one in here?
Everything between negative 1 and 1.
Yeah, the first one is going to be S sub 1, and then we're going to have S sub 2, and then we're going to have S sub 3. ... going on forever. This is an infinite collection. Nothing wrong with that. But if we write those out concretely, like you were just thinking, then S sub 1, when we plug in 1 for n, that goes from negative 1 over 1 to positive 1 over 1. So that's a closed interval, negative 1 to positive 1. And then the next one, when we plug in 2, that's the closed interval from negative 1/2 to positive 1/2. And when we plug in 3, that's negative 1/3 to positive 1/3. ... and we go on forever. This is another example of a nested collection, because this is always a subset of that. This is a subset of that. The 1/4 one would be a subset of that. On a number line, we're zeroing in. So if we were to draw this on a number line, here's 0, here's negative 1, here's 1. We start out including this, starting here, going all the way over, including all the numbers between negative 1 to positive 1, those numbers. But then the next set only goes from negative 1/2 to 1/2, so it just includes those numbers. Then negative 1/3 to 1/3, then negative 1/4 to 1/4, 1/5 to 1/5, blah, 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 blah. Negative 1/100 to 1/100, zeroing in on 0. So there's another example of a nested collection of sets. Any questions on those before we move on? Okay, more definitions. Definition of union. So if U and V are set, U union V is a set of all X where X is in U or X is in V. We've already seen that before. Similarly, U intersect V is a set of all X where X is in U and X is in V. If we draw those pictorially, if this is U and this is V, U union V would be all this, but U intersect V would be just those spots, just the portion that's in both U and V. So U union V, the whole thing, U intersect V, just that middle part. Now we can union up one of these index sets. If I have a set like this, I can union up all the elements in that set. Going back concretely to this set, remember what this set was. This was a set of all the students who are at least 14, and all the students who are at least 15, and all the students who are at least 16. If I were to union all those sets up, what would I get? I'd get all the students in high school if I union all those up. So that's what this is defining the notation of. We're going to union for each little d and big D, U sub d, where U sub d represents one of those sets. Maybe I should have used an S here.
Basically, if you had an index collection, pick every kind of sets and put them all together.
Yeah, it's unioning up an index collection. So for each index in the index collection, take that its associated set and union it up with the next set. So let's look at its exact definition now we have intuition for it. It can be the set of all X where there exists some D in our indexing set such that X is in S sub D. So there has to be some S sub D that contains X in order for X to show up in the union of all those sets. If we unioned up all the high school students, I would not be in there because I don't show up in any of these sets. And I think we switch to S and S to help keep our notation clear. So when we union it all together, for an element to show up in the union, it just had to show up in at least one of those sets. So when we do the union, it's going to be all the X where there exists at least one indexing element such that X shows up in the set associated with that indexing element. On the other hand, what's the intersection going to be? Has to be in all of them. So if I were to do the intersection of all these sets, what would I get?
Yeah.
No, I'd get S sub 20.
Only if it's at least. You're doing the at least, right?
Yeah, with the at least that we have here.
Oh.
Oh yeah, we switched it while you walked out. As an example of a nested. Thank you. Nested. Anyways, yeah. So if we took all the students who are at least 14, and at least 15, and at least 16, and at least and at least 20, you're left with all the students who are at least 20. So it has to be the students who show up in every single one of these sets. So the intersection of all of them, the intersection for every little d in big D of S sub d is equal to the set of all X such that for every element in our indexing set, X is in the associated set. X has to show up in every single S sub d that you have in your collection in order for it to show up in the intersection. Notice that this would be identical going back to how we wrote this in set theory, because we did the union of a set of sets in set theory, and we did the intersection of a set of sets in set theory. Using set theory notation, this would just be the union on S sub d, or the intersection on S sub d for each little d in D. So this notation is just putting for each little d in D there. By going back to set theory, we had this notation already defined and this notation already defined. We just didn't use the indexing set like this. But we know that's a set of sets, we know that's a set of sets, and we know how to union them and intersect them from set theory. So exact same definitions here as we had in set theory. It's just moving that there, moving that there. Okay, example. Let's union up for every town in the set of all towns, in the town big T, big T, we're going to reference this example here. So using the example we have right here, it's okay if we call our towns 0, 1, and 2. That's fine. So let's union up for each little t and big T, the associated b sub t. What would we get here? We get Bob, Frank, Jack, Bill, how many did I get right? And Dave? Is that it? And Dave. All right, we get all the barbers who show up in at least one of these b sub t's. So all the barbers that show up here or here or here. On the other hand, what would we get if we intersected them all? We would get the empty set. What would it mean for someone to show up here? It would mean that they were a barber that worked in every single town. Now let's pretend for a second that it was just T0 and T1 there. Then who would we get? Bob. Between 0 and 1, Bob works in both. So in that case, we would have gotten the set containing Bob. He's a barber that works in all those towns. Okay.
You do the same notation as your special case, where you can say starting at this number and going up to this number.
I see what you're saying.
If they were numbered.
You're thinking like you have with the sigma notation.
Yeah.
I don't know if we'll see that notation.
Something may or may not exist.
I mean, if you were to use it, I think most people would understand what you meant. I don't know if that notation shows up in this book, though.
They would have to be ordered somehow. You have to have a.
Yes, they would have to be ordered somehow.
With that special case.
Right, it'd be the same exact restrictions you have on the sigma notation. Yeah. Okay, let's look at this example. So we're looking at the union for every positive integer n of negative 1 over n to 1 over n. We union up all those intervals, what are we left with? We union up all those intervals, what are we left with? This would just be negative 1 to 1.
Yeah, if you intersect.
That closed interval. And then you're looking down at intersection. If we intersect all those, then we get what?
You get closed interval.
The set containing 0. So one element set, infinite element set. Okay. I think we're good on that notation. All right, another thing that we already defined earlier in set theory, but we'll define it again. If the intersection of two sets A and B is empty, then we call A and B disjoint sets. Also, if you have some index collection of sets such that for any two indexing elements that are not the same element, the intersection of their associated sets is empty, then the entire collection is called mutually disjoint. Or in other words, I have this collection of sets. If for any two sets I choose in there, as long as I didn't accidentally pick the same set twice, for any two sets I pick in there, if I take their intersection and it's empty, then we call the entire set of sets mutually disjoint. In other words, none of the sets have any elements in common. If we go back to over here, the set with the students, these are not mutually disjoint sets. Because if Jill's 15, she shows up in this set and this set. But if we switch it from at least D years old to is exactly D years old, now these are mutually disjoint. Because each person can only show up in exactly one of those sets. It's impossible for a student to show up in two of those. So that's disjoint and mutually disjoint. And I get that you get the concept. Try and make the concept appeal to, try and get try and understand the way it's actually written here as well, and see how that tells you what you already understand to mean. Because you get it's mutually disjoint. Make sure you can read the notation and say, oh yes, it's saying that it's mutually disjoint. So we're saying that if this is an index collection, such that for any two indexing elements you choose, m and n, as long as they're different, then their intersection of their associated set is empty. That's the same thing as saying for any two sets you choose in here, their intersection is empty, then we call it mutually disjoint. So make sure you can go from the notation to what you already understand we're trying to say. Because the notation, that's what kicks you at first. It's just dense notation. D is what we're indexing on. Yeah. It's little d and d. Okay. Any questions on disjoint or mutually disjoint? Okay. Let's move on now to our first proof of topology, called the union lemma. The union lemma is going to sound stupid simple, but it turns out to be absurdly useful. And we're going to use this lemma all the time. So let me give you intuition for it. It's saying that if we have some set x, and for each element in x, so x is composed of some elements. For each element in there, we'll pick a particular one called little x. If for each element I choose in there little x, I can find some subset of x called u sub x that contains that point. So here's u sub x. For this point x, u sub x is that. If for each little x and big X, I can find some subset called u sub x that contains that point, then the union of all the u sub x's is just going to give me x. So for that point x, we found that u sub x. For this point y, we find some other subset u sub y. And for this point w, we found some other subset u sub w. In this case, u sub w happened to be u sub y. Maybe they're the same, maybe they're different. Notice u sub x is different from u sub y, but u sub y happens to be the same as u sub w. So for any element I can find in x, if I can find some subset that contains that element, unioning up all those subsets gives me back my initial set. Sound straightforward? If it sounds obvious, then you got it. If it doesn't sound obvious, I'm not saying it good. Let's do just one concrete picture where it actually works. So here's x. It's composed of the elements A, thinking when I wrote that point, A, B, C, and D. We've got this subset here, which we'll call subset A, and we've got this subset here, which we'll call subset B. Notice that for each point in x, we found an associated subset that contains that point. Then we're saying x is equal to the union of all these sets. The union of all these sets, A and B. Very concrete picture. Okay, so let's read it up here now, make sure it makes sense. Let x be a set, and let C is going to be our collection of subsets. And let C be a collection of subsets of x. If for any little x and big X, if for any point we choose, there exists some subset u sub x in C, there exists some subset like A, there exists some subset u sub x in C such that x is in u sub x, then the union of all those u sub x's just gives you back the initial set x. Okay, let's prove it. Assume you antecede it. So what am I going to do? I'm going to assume that this is the case and show that these two sets are equal. So assume that for every little x and big X, there exists some u sub x in C such that x is in u sub x. Okay, we assume the antecedent. Now, I need to show that this set is equal to this set. How do I show two sets are equal? All right, show that they're subsets of each other. So I need to show that anything you choose in here is also in here, and then anything you choose in here is also in here, and so they're equal. So let little a be an arbitrary element in here. Now, if little a shows up in the union of all these sets, then little a must have shown up in one of those sets that were union together. So let a be in the union of all the sets, and observe that there must have been some x sub prime in x such that a is in u sub x prime. Or in other words, there must have been one of those sets in there, a must have been in. One of the sets that we're unioning up, we'll say its indexing element is x sub prime. Maybe x sub prime is a, maybe it's not. The same way that this b here we could have called u sub c. Were we using u's? Yeah, we could have called this one u sub c, which is the same thing as u sub b in this case. And we could have called this one u sub a, which is the same thing as u sub d in this case. So we don't care where that is. Observe that there must exist something in there that's associated with a subset that A is in. Since A shows up in the union, it has to show up in one of those subsets. Then, since u sub x prime is a subset of x, A has to be an x. A is guaranteed to show up in a subset of x, therefore A has to show up in x. Pretty straightforward thinking.
How are you seeing something?
How are these two saying something different?
Your line 2 and 3.
Line 2 is saying that since A is in the union of subsets, A is in a particular subset. Line 3 is saying, and since the particular subset is a subset of X, then A is in X. Could have combined it all in one line if you wanted. I'm stretching out this proof. If you look at it in the book, I'm sure the author writes it down in 3 sentences. Okay. So we just barely showed that for any little a you choose in here, it's also in big X. Therefore, the union of all those sets is a subset of big X. Now we need to show the other direction. We need to show that big X is a subset of this. So let little a be any random element in big X, we're going to show it shows up in the union. So let little a be any element in big X, and observe that by assumption. Remember, we assume that for any little x in big X, there must exist some set in C that contains it. So little a is something in big X, so there must be some u sub a in C such that a is in u sub a. It has to have its associated subset. By assumption. That's what we assumed was the case. So then, since A is in U sub A, and this is a union of all those subsets, then A shows up in the union of all the subsets. Since A shows up in a particular subset, A shows up in the union of all the subsets. And so, X, big X, is a subset of the union of subsets. We showed that for any little a you grab in X, it also showed up in the union. Therefore, big X is a subset of the union. And we showed the union is a subset of big X is a subset of the union. Therefore, they're equal to each other. That's what we meant by set equality. Both sets are subsets of each other. All right, there's the union lemma. It's obvious it's a fills. We're going to use that 100 times in this class. As obvious as that fills, we're going to use that 100 times in this class. No, not a field. We won't be working with fields. Okay. Any questions on that? All right, next definition. Set difference. I think we already covered this one. A minus B, that's a set of all X that are in A but not in B. Drawing a picture of it. This is A, and this is B. Everything that's in A but not in B, that's the stuff over here. A minus B. Notice that's very different from B minus A. That would have been all the stuff over here. So A minus B different from B minus A. All right, question. If A intersect B is the empty set, then what is A minus B equal to? Just A. If A intersect B is the empty set, that means we have a picture like this. That means they're disjoint. Here's A, here's B. Take all the elements in here. Now remove all the ones that are also in here. None of them are also in there. So you're left with what you start with. On the other hand, if A is a subset of B, then A minus B is the empty set. If A is a subset of B, then that means our picture looks like this. Here's B, and A is a subset of it. It's inside of it. Take that, now remove everything that's in here. You remove the whole set. Wonderful. All right. Next, cross product. For Emma from last time. So the way that the set theoretical definition that you're supposed to use for an ordered pair with the way I was developing set theory was this. AB is equal to the set A, comma, AB. So if we use that domain for our cross product, then this is how we were supposed to define the ordered pair. If we define the ordered pair a different way, we're supposed to use a different domain. So I was using a domain when we use one definition with a different definition of ordered pair. I wasn't using an author. It's my own notes. And so I just took my notes wrong. Because when you go look at like a Wikipedia page, it's going to be listing 3 different set theories at the same time. So I just wrote the wrong definition down for this.
I didn't realize there were so many definitions for different.
Isn't that the exact reverse of that, right?
Before, we had it like this.
Okay. Yeah.
And that's called the short notation, and then the notation that you're supposed to use, this is the most common one, actually. More common than the short one. And it's some name. I don't remember the name. So that was the problem we had last time. Yeah, there's logically equivalent definitions. We spent a lot of time talking about the 2 different ways we could define the natural numbers. And one was the older way, one's the newer way. They're logically equivalent. One's just nicer to work with. Okay, so ordered pair, cross product. We've already defined this, but define again. A cross B, what is that? It's a set of all ordered pairs, x, y, where x is in A and y is in B. Keep in mind, this is in no way an interval of numbers. This is now an ordered pair. Unfortunately, we have used this notation all the time. Concrete example. If A is equal to set 1, 2, B is equal to set 3, 4, A cross B is equal to the set of ordered pairs 1, 3, 1, 4, 2, 3, 2, 4. All the ordered pairs we can get where the first element comes from this set and the second element comes from this set. Question, how many elements are in 1, 3? 2, if we're talking about the ordered pair. If we were talking about the open interval 1, 3, how many elements are in there? Infinite. So you have to infer what this means from context. If we were just talking about ordered pairs and cross products, obviously we meant that as an ordered pair. And we can take the cross product of however many sets we want. I can take the cross product of n sets. So I can do A1 cross A2 cross A3 cross A4 cross ... however many we want. What is that? It's going to be the set of ordered n tuples, where the first element comes from the first set, and the second element comes from the second set, and the third element comes from the third set, ... and the nth element comes from the nth set. And a common place we see this is in relation to the real numbers. So if I do R, that's a set for all real numbers. R cross R, what does that give me? Gives me all the ordered pairs of real numbers. Or in other words, it gives me the plane. Yeah, so this gives me the coordinate plane. And that's why we represent a point in the plane with an ordered pair. 1, 3, or whatever. If that was like that. 1, 3. Because we're doing R cross R. And if we did R cross R cross R, what do we use that to represent? 3D space. 3D space, we need 3 coordinates to specify where a point is. And so that's what R cross R cross R is. And R cross R cross R cross R, that would be for just 4D space. Nothing about time, really. Yes, a space-time is a 4-dimensional logic. Make some words there. Space-time, the mathematical object of space-time, is a 4-dimensional topology. So, yeah, you could use it for space-time. The definition of a spacetime? In studying general relativity.
They treat it as a mathematical object. That's what it's asking about. To me, it sounds like there's math class for
I'm sure that there are.
why
Yeah, a spacetime is a mathematical object. The type of manifold, is a type of Hausdorff topological space, is a type of topological space. And so we find out what topology is first, and we can work our way out. Okay, so there's examples of using these cross products to give you some intuition for them. Anything else on this before we move next board? Kind of flying through this. You guys aren't asking enough questions that people would normally ask. Yeah, I've taught you guys too many times. Yeah, if you were there for our first topology course, because we used it 100 times. No. Okay, that's got the whole board. Okay. More theorems. Theorems on sets. Remember in topology, we're very low level. We are going to be working with sets directly a lot. And so these theorems are actually going to be really useful for us. So we need to get at least some good intuition for each of these theorems, and we can prove whichever ones you want. But first, let's draw a picture of each one of these and make sure it for sure appeals to our intuition, and then can show you how we go about proving any of these. Or you guys can prove them, I guess. All right, but not button that. Let's draw pictures for each one of these real quick. So A intersect B union C. So we've got some set. Here's A. Here's B. Here's C. They potentially intersect each other. So we have A intersected with B union C. So first off, B union C. That's this whole set and this whole set. And then we want where they intersect with A. So that is going to be this portion right here, right? Now, let's read the right-hand side, and I'll color in the right-hand side the other way. Hopefully, we're coloring in the same space. So the right-hand side is everything that's in both A and B. So A and B, that's this portion. Together with everything that's in both A and C. Both A and C, that's this portion. And so, yay, we colored in the same spot twice. Or if you think about it, in terms of their logic equivalence, remember that intersect acts a lot like an and union acts a lot like. So if you have A and B or C, that's the same thing as A and B or A and C, which is how I would have thought about it. But pictorially seeing it is probably what's best for most people, so we'll keep doing that. All right, let's reset up our picture now. So we have A, B, C. We need to start with A union B intersects C. So we for sure have all of A. And we're going to union that with B intersects C. So B intersects C, that's this middle part right here. So we include this. A union B intersects C. Gave us that. All right, let's look at the right-hand side. We have A union B intersect A union C. So A union B, that's both these circles. Where they intersect A union C, both these circles. And that gives us all of A and then that again. Okay. Pictures with cross products, kind of hard. Because when we pictorially represent these, each time you cross, you want to add another dimension to help you see it. If we think about R, we think about that as a real number line. R. When we do R cross R, that's taking that line and crossing it with this line, R cross R. And now for each point on here, we need to associate a point that lines up with each point on here. we need to associate each point on this with an entire line of its own. And it ends up coloring an area. So pictorially drawing these, I'm going to draw a little bit funny. Hopefully you get used to the funny drawing to help you see it. So we're going to do A cross B union C. So here's A. A I'm going to represent as a line. Since I want their cross product to be two-dimensional, I need to represent each of the sets as one-dimensional. So we'll do A on the y-axis like that. And we'll say B is this. And we'll say C, if we draw them both in the same direction, we're saying that they overlap each other. So I'm saying that overlaps that. You with me? Yeah, think about them as line segments, but if they line up horizontally, then we're saying they have the same points. So B intersects C. Or, I don't know how else to draw it. Maybe I can do it like this. Draw them all the same, and then say B starts here, and it goes over to here, and then C starts here, and it goes over, let me do that. C, okay. So B is that portion of it, and C, maybe give it more overlap so it's obvious, and C is that portion. B is from here to here, C is from here to here of this set. And this is my set of all objects. Okay. So we're looking at A cross B union C. Well, B union C gives me this whole thing. Let me redraw A being up here. A is these points. So when we think about A cross B, that's going to be all the points like this, crossed with all the points like this, gives me this area. This is how we would do A cross B union C. So that's A cross B union C. Now let's compare that with A cross B. So here's B, here's A cross B. That's going to be this. Here's A cross B, with me? Union together with B or C cross A. So C cross A cross C, that's going to be all this. And notice that when it's all said and done, we end up with the exact same rectangle. So that's pictorially how we have to think about cross products, or at least how I have to when I draw out a picture of it. All right, so that was the third one, right? So the fourth one, it's good to have those dotted lines. Maybe a dotted line for where C goes and a dotted line for where B goes. Okay. So now the next one, we are looking at A cross B intersects C. So B intersects C, that's this portion right here. When we cross that with A, that just gives us this inner rectangle right here, right? B intersects C is that portion of it. And we cross that with A, gives us just that area. And then we're saying that's equal to A cross B intersect A cross C. A cross B is this rectangle. A cross C is this rectangle. Where those rectangles overlap is just that middle part. So pictorially, yep, that's the same. A cross B minus C, let's look at that. So if we have B and we get rid of everything that's in C, then we're left with this portion of B, right? So A cross B minus C, that is this rectangle right here. Compare that with A cross B minus A cross C. So A cross B would be this rectangle. Then we minus everything that's in this rectangle, and we're left with that same portion. So that makes sense? So that ends it for our having to draw two-dimensionally. Now we have A minus B union C. So let's go back to our Venn diagram. A, B, C. We want A minus B union C. So we start with A and we remove everything that's in B or C. That leaves us this top part. And that's the same thing as A minus B intersect A minus C. Let's look at that. So A minus B leaves me everything in A minus that little portion. A minus C leaves me everything in A except for that little portion. Take the intersection of everything but that portion and everything but that portion, you're left with that. So that's the same. And then finally, A minus B intersect C. So A minus B intersect C, that's going to be everything except for not including this little part. A minus B intersect C. That's the same thing as A minus B. So A minus that portion, union together with A minus that portion. And so the only part we didn't include was that little piece. Okay, so that's pictorially going over each one. Hopefully that helps appeal to your intuition. Now let's prove them. I'll prove whichever ones you want, as many as you want, and then you guys can do whichever ones you want.
Go around.
All right, you just want me to do the first one, then we just go around from there? Okay, so the first one, I'm proving that this is equal to this. I'm going to start with this and keep messing with it until it looks like that. So I start out with A intersect B union C. Okay, what is this equal to? And I'll kind of do it the long way the first time to thoroughly show all the steps.
We have the definition up there.
Yeah. So what does it mean to intersect two sets? This is a set of all x such that, maybe we should do this one first.
Yeah.
I think you'll be fine either way, but I think this will be more proper. This is A intersect. Let's plug in this definition. We got to do that one first. Parentheses, right? Union those before you intersect, blah, blah, blah. So this is A intersect. Let's write this out. Let's B union C. That's a set of all x such that x is in B or x is in C, right? Okay, now plug in the definition of intersection. This is a set of all x such that x is in A and x is in this set. But we already know the qualifications for being in this set. It's written right there. So that's x is in B or x is in C. Right? Distribute an and over an or. Have we already talked about how to do that in this class?
I don't know about this class.
So
You have to do like a lemma.
now I'll let you guys just do the logic after this, but we'll write it out once. Alpha, beta. So we want to, we need 3. Right? Gamma. And so we are trying to show that alpha and beta or gamma is the same thing as alpha and beta or alpha and gamma. And that's how you distribute an and over an or. So let's show that really quick.
We did this in logic.
I don't remember if we did it. True, true, false, 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 false. I know we distributed a not over each of them, but I don't know if we distributed an and over an or over an and. True, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Okay, there's all the possible 8 combinations of alpha, beta, and gamma. All right. Now let's just evaluate it in each of these cases. So if they're all true, then this obviously evaluates to true. If we have true and true or false, true or false is true, true and true is true. Right? Same thing for the next one. If we have true and false or false, that gives us false. And then for these next 4, if alpha is ever false, the whole thing's false. So, sorry, I really slanted. False, 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 false. Hopefully you can follow my table there. That's terrible. Okay, over here, obviously if they're all true, we get true. Next, if they're true but our gamma is false, so true and true is true. True or anything is true, so we don't even need to evaluate this one. Right? Over here, true and false is false, or true and true is true. False or true is true. Okay, next one. Alpha is true, but the other two are false. True and false is false. True and false is false. False or false is false. And then, if alpha is false, this whole expression is false, and this whole expression is false. False or false is false. So it's false in all the other cases. And surprise, surprise, we get identical things. So, trying to come up with a sentence really quick to make it obvious. If you're looking at a menu and you know you got a burger and fries or salad, then I know that you got a burger and fries or you got a burger and salad. Okay. Similarly, we won't write this one out, but when we distribute an or over an and, it works the same way. That becomes or, that becomes and, that becomes or. So now it's a really weird restaurant. You can either get a burger or you can get both fries and salad. Then we know that you got a burger or fries and you got a burger or salad. That one doesn't sound very good. What's a better way to say that? I don't know. When I stand here, I sometimes just blink. Maybe I use the markers. Let's try and come up with a marker example. Good practice for when you're teaching next year, right? Yeah. All right.
I don't know, you don't usually use 3 markers.
Alpha's the black, beta's the blue, gamma's the red.
Yeah.
So we're saying I'm holding the black marker or I'm holding both these markers. Then I know I'm holding the black or blue and I'm holding the black or red. So I'm holding these two and I'm holding these two. That still doesn't click with the intuition good. There's got to be a good way to make this click. I know I have a good example somewhere. I didn't come prepared for logic, so I didn't think about it ahead of time. Well, I'm done trying to think of good examples. Hopefully it clicks. Okay, so anyways, very important.
You probably could have done swans without. If you have a third one, third element throws it off.
I'm not going to worry about it anymore. You can prove it to yourself if you want to. Write your own truth table. Okay, very important. No, X is in A is a proposition. X is in B is a proposition. X is in C is a proposition. So we have propositions and logical operators. So we're in the realm of propositional logic when we manipulate these things.
Right.
Should have made that very clear. And so we can use all our rules of propositional logic. Okay.
Well,
So
you also have
So this is like my alpha, that's like my beta, that's like my gamma. And I know alpha and beta or gamma is the same thing as alpha and beta or alpha and gamma. So this is alpha and beta or alpha and gamma. Right? And now, X is in A and X is in B. That's the same thing as a set of all X such that X is in A intersect B. If X is in A and X is in B, that's the same thing as X is in A intersect B. Right? Or X is in A and X is in C is the same thing as X is in A intersect C.
Did you need to put that instead of notation? Get that straight to the end result.
I mean, technically in the steps of a proof, you can always skip to a step. It's just a matter of can your audience follow everything that you're saying? So what does it mean to be in A and intersect B? It means you're in A and you're in B. Okay? And now if you're in this or you're in this, that's exactly what I mean by union. Right? So that's the same thing as A intersect B union A intersect C. What's the definition of this set union this set? That's a set of all X such that X is in this or X is in this. So we show that this is equal to this. Okay, so that's the first one. All right. Who wants to do the second one? All right.
I mean, it should be pretty much the exact same as what we said. Just different. Working hours and ends.
Yeah, that is very similar. Cross product's not much different than and. So A union B intersect C. That's what you're trying to show. Yep. Okay. A union B intersect C is equal to curly bracket. A union the set of all X such that X is in B and X is in C. Okay. So now you union them together. It's going to be the set of all X where X is in the first set or X is in the second set. Good.
This turns into your or A and B or A and C. Where did I get that backwards?
Yeah, notice that it's true if x is in A or x is in both these.
Yeah.
If x is in A, this is true.
Yeah.
And if x is in both these,
It's
then
true.
this is true.
I was just, yeah. Thinking of case where it's in A and B but not C, but I realized that it's not. This X is in A or that. Then I would use my conditions and go back to X is in A union B. X. Oh, at this point, I guess I'll get rid of this. That turns into B union B. X. C.
Yeah, replace your ors with unions and your ands with intersects. All right. B B union C. A cross B union A cross C. It distributes just like times does over plus. Yeah, you'll notice that the times distributes exactly how you would expect it to.
Yeah, we did go over this.
We probably did some of it. I don't know that we did all of it, and I don't know that we took the time to prove any of them. Probably just talked about them.
So A cross B union C means A is in, or all the order pairs X, Y, such that X is in A and Y is in B.
Right. Set of all x, y, where x comes from the first set and y comes from the second set. And y being in B union C means that. Good. Right, so almost the exact same as the first one. Like you have alpha and beta or gamma. Same thing as alpha and beta or alpha and gamma.
And then when you have all ordered pairs X and Y such that X is in one set and Y is in the other, means
I understand what you're saying. Strictly speaking, that notation's nonsense, though.
yeah, right.
You'd have to say the set of all xy, where xy is in A cross B, or no, just where the order pair xy is in. Yep. Because your element now is just an order pair rather than just x.
Right.
Now you have your set of all elements, where that element is in the first set or the element is in the second set. That's the same thing as the union. It's still going to be order pairs xy. I think you're done writing out set builder notation. Wonderful. All right, so I do the next one. Yeah, it's pretty much the same. Let's see if I can whip this out. Whoop. Oh, wait, that was an and. Whoop. Whoop. Now, oh, you're saying up here what we're trying to prove? Okay, we're trying to prove that. All right, so we got to here. Now we got to use a piece of logic, which is adding a proposition onto it itself again doesn't change anything. So alpha and beta is logically equivalent to alpha and beta. So I can add and on another x's and a. So these are all ands. And I know that and is commutative and associative, so I can put them in any order I want, in parentheses in whatever order I want. So x is an a and y is an b is the same thing as x is an a cross that. This just becomes an and. This just becomes an intersect. And we're done. So since that was so easy, I'll do the next one. How many do we have? So I'm on this one, right?
If I said you gotta let me do a hard one.
Did I skip?
No, you just solved the fourth one. Now we're on the fifth one.
Oh, you want to do a hard one? I would guess that this is the hardest of the bunch. So. That's the hardest of the bunch.
They've all been pretty simple.
Okay.
I had to do a little thinking on making sure that
Well, I'll let you struggle your way through this one.
make it sound like it's gonna kill me.
I think you'll survive.
I might just get stuck. Well, let me draw my picture just to make sure I have it.
Sure. Yeah, do whatever you gotta do.
We'll just do it right
There's A,
here.
B, C.
Go like
Sure.
way there, guys. Got the buttons reading aren't that great, I guess, but we have A cross B minus C. B minus C is going to be all this stuff.
But we're crossing it with A. Oops, so your spawn part. Yep. Okay.
Same as A cross B, back A cross C. Yep. Sure enough,
Okay, there's your picture.
that picture, I can make sense of it. Guess I could have done that a little more. All right. A cross B minus C to A cross B, subtract cross C. Here, I should probably just do that back across the lines. Minus C to A cross all.
Yeah.
I can do it like this first. Doesn't matter either way, right?
No, that's strictly speaking, this is a more proper way to do it.
Okay.
Replace the inner parenthesis one before you do the outer one.
Right. What's the exact definition?
It's a set of all x where x is in the first set and not in the second set.
But I'm afraid that I'm going to notate that differently.
Just and x is
Okay.
not in C.
Yeah. Okay.
Okay.
And we're going to get a set of ordered pairs.
I would have used y for your second one.
So it's not yx, it's xy.
Yeah.
Okay.
I think that'll help you not confuse yourself.
Yeah, that's probably true. So this will turn into the set of all x, y such that x is in A and y is in B and not C.
Right. Yeah, it'll
Doesn't
probably
really
help you
matter,
keep
but-
track of it.
Yeah.
Okay.
Now I have to get back into this.
Yep.
So I need to distribute my and essentially.
All right.
So this will be x. Yes. Yeah. X is A and y is B and x A. Right?
Yeah. Okay.
I mean, it's as if I were saying x is in A twice.
Right. Yeah. Yep. You're perfectly fine with what you're doing.
I'm just skipping a step.
No.
Oh, okay. I'm on the right track.
What you have is perfectly valid.
What you're saying it's the minus that's throwing me off. I got to show that. So basically, I need to double knot this, or write it in a different way. This is gonna, okay, if I were to just scratch work, this would turn into A cross B.
I would do your scratch work lower down
Well,
because you're probably gonna want to reference it when you come back in and fill it.
okay, that's fair. A cross B, and then this is
Minus
an
A cross
intersection,
C.
which is not what I need.
Oh,
A,
I thought you were gonna reverse engineer it.
I'm going to. Well,
Okay.
I'm trying to see what I have.
All right.
A cross, not C. So A minus C. Is that the way that works?
No.
No.
A minus C is a one-dimensional thing.
Yeah,
You're
it
saying
is.
X in A
A cross
and
not
Y
C.
not in C.
I don't know. Are you sure to do that? Maybe you gotta take your advice. Okay.
So A cross B minus A cross C. What would you need to get
I
that?
have X in A and Y in B minus X in A and Y in C. Okay, now it's minus.
Yeah, you're okay.
I'll probably get back to that. That's valid, right?
Sure.
So this turns into everything that's in here and not in here.
Right.
So that's kind of what I have.
Okay.
So I get essentially X in A and Y in B and not X in A and Y in B. This is the same thing there. And knotting over here will be not A or not C.
Right. Not alpha and beta is not alpha or not beta. So X not
is
in
not
A.
in A or X or Y, I guess. Not. Now that is what I don't have, which is probably why that was a bit of a red flag, I guess. So
So you see, you have your left part.
how do I get a not A?
So all you're missing is your X not in A.
Yeah.
So maybe if you erase this,
And try this again.
notice going from here to here, all you did is you used a substitutivity.
Yeah.
Okay. And you need this to be an or. Ultimately, you need to somehow justify or x not in A here.
Is there like a conjugate positive?
Well, we know that A or not A is always
We know A or not A is always true.
So I could change that here and make this the longer statement. X is in A or X is not in A.
That's oring it with it. Notice that what you need there is an and.
Right here. That's it. Should be or.
That your x is in A is over here, and you're anding it with. You can try to do it. I don't think it's going to work like you think.
Probably not.
But I'm all for you trying whatever you want.
Well, I don't think that it's valid. Can I just insert that in here? X is in A and then insert or not in A.
It's always the case that x is in A or x is not in A. That's a tautology, so you can always assert
I
that.
can always insert that.
Sure. Just not sure it's going to get you where you think it's going to get you. I don't know. Did you already work it all out on paper? Get anywhere?
Yeah, but I made an assumption that I don't know if it's valid.
Okay.
Just like so you can see it's not this set.
There's
Okay.
another way I rationalize it.
You're saying you didn't choose this route at all? You chose a different route? Or?
Well, what you need to just justify putting this
I'm trying to figure out
right
how to
here,
justify it.
right?
Maybe let's do like a side.
And the justification is that x, a proposition, we'll say alpha. Alpha is always equal to alpha or false.
This is what I have. This is what I had. Right? That was what this was.
That's what you had before, yeah.
Okay. Somehow,
Oh, what are you doing?
I'm just doing a little side below.
Okay.
Maybe if I see it together, then I can, I don't know.
No, those two are not going to be close to the same thing.
Well, that's what I'm trying to show. So.
You're trying to show
Something's not right.
you have to use all your information to justify what's going to happen here.
Yeah.
X is in A and Y is not in C is in no way close to X is not in A or Y is not in C.
Okay. So there's another thing that I need to justify. It's going to be outside of this little segment. It's going to include something else.
Make sure that this clicks with your intuition.
I mean, I don't really see it.
Okay. X is in A and Y is in C. So draw some two-dimensional picture. That will always help. So we've got this is A, here's C. Okay. So we want a point that's in A and not in C. In A and not in C. That would be a point like right here.
Yeah.
There's a point in A and not in C.
Not in C or not.
A and not in C is going to be this area and then this area.
Right. If it's
And then
not
over
in
here
A,
we have not in A or not in C. Here's a point that's not in A or not in C,
those are not in C.
which is very different. Okay. So you're not going to be able to manipulate just what you had here and make it equal that.
But this point, oh no, that's an and, it's not an or. Okay.
Even if it were an or, it still has problems.
If it were an or, then at least this would be included in that. But if it didn't capture all the
If
information.
you're an or, then you're saying X is in A or Y is not in C is the same thing as X is not in A or Y is not in C. That part cancels out, and you're left with X is in A is the same as X is not in A.
Okay. Not better.
No. So that thinking that you're using, no, you're not going to be able to do it. You're going to have to take a holistic view of all your information.
Is it? I wonder if it's better if I just erase this line and go back here and try.
Look, you know what you're missing.
Yeah, I do.
You know that you need to or this with X not in A.
Yeah.
That's all you need to do.
Yeah.
So you need a way to justify that you can add that little piece. So how can we justify simply adding x is not in A or that? So we're ORing this with that. That's what we need to justify.
Right.
Now, we know that alpha is always logically equivalent to alpha or false. I can always OR alpha with a statement that's always false.
Okay.
How can I justify x is in A is always false? Or sorry, how can I justify x is not in A is always false?
Because we said that x is in A.
Because x has to satisfy this thing over here.
Yeah.
This thing over here says x is in A.
Well, and so does this. I mean, you
Right.
just distribute
Okay.
it.
So we know for x to satisfy our condition, x has to be in A.
Yeah.
So if we say y is in C, or y is not in C, or x is not in A, ORing the x is not in A doesn't change anything, because we know x is in A.
Okay. So how? So in my distributing.
No, it's not any distributing. The rule that you're using is you can OR a statement that you know is always false.
Yeah, but how do I go from here to here? If I were to erase this, how would I? Oh, because associativity
Yeah, so here to here without that
is just
is just associativity.
Oh,
And then ORing that piece in
yeah.
is just ORing a false statement.
That was pretty simple.
But that ORing a false statement, that's a bit subtle.
That is a bit subtle.
I think it would have been easier for you to start with the right-hand thing and show it's equal to the left-hand thing.
Well, yeah, but you don't know that until you try it necessarily. I mean, until you think about it.
Yeah, I'm saying I think it might have been easier for you to remove that and say this is only going to be true when this part's true.
Yeah.
Because x has to be in A to satisfy this part.
So from here, this goes to here.
Right.
And we're done.
Yep. There she blows.
I wonder how long it would have taken me to get that little realization on that. Would have just taken me 2 hours.
I've done weird set theory proofs like this with some of my university teachers before, and we've gotten stuck for hours on stupid things like that. So it can be hard to think of.
I can tell you realize it. I mean, that's not something that's difficult to understand, but you might not think about it.
Right. You don't get it for free just by doing some propositional logic manipulations like you want.
Yeah.
And so you have to use information already given. Okay. So that settles that. All right, Emma, I think you're on to the next one.
Number 6.
Sure.
Yeah.
You haven't started indexing by 0 as a programmer?
Oh yeah.
That's in slot 5. A minus B union C is the same thing as A minus B intersect A minus C. Yeah, that one you gotta think about for half a second. Not just obvious. Take A and we minus B or C, that's the same thing as taking A minus B and A minus C. Okay.
Actually gonna do what's distributing the not.
Okay. So A minus the set of all X. Oh, is that what you were saying? Oh well. Doesn't matter how you do it. As long as you do it right. Right?
Right. Well, as long as it's
Well, makes sense to you and makes sense to me can be two very different things.
I know, but
Getting to the end of the proof is always real easy. Let antecedent and therefore conclusion. Square box.
Kind of a roundabout way of doing it. Not in the set of all x is satisfied.
No, how you have it is right. It's just
Oh,
minus.
you're right.
That's a set operation, so you need two sets. A minus that set. That's perfect.
Set of all x.
Where x is in the first thing and not in the second thing. And just not those things. And not parenthesis x and b or x and c. If you want, like, just flat out using definition. Yeah. B or x. Not in B and x not in C, yep. So distribute a not over an or, turns it to an and. Now since they're all and, you can do it however you want. All right, alpha and beta is the same as alpha and beta. So we can add x is an A to it again, and it doesn't change anything.
All the skip this step here. X is in.
Oh, yeah, good catch. Well, x, where x is in A minus B, and
X is in
C. Good. Yeah.
It is A minus B.
Intersect. Okay. And then I do the last one. Yeah, let's see if I can pull this off. So that is going to be, we switch this to, oh, that's what she's printing. Oh well. And that should be a union. Oh, okay. Sorry. Went weird in my brain for a second. Okay. A minus B intersects C, B intersects C. That's the same thing as all x in B and x is in C. Now, A minus that is going to be x in A and not x is in B and x is in C. Distributing a not over an and switches it to an or. X is in A and not x is in B or x is in C. Let's see, going from here to here. Uh-oh, we're in trouble. Can't just do that. When we distribute an and over an or. Okay, so I think from here we need to erase, right? I think it turns out it works. Okay, yeah. Distributing an and over an or, so we get this and this, or this and this. So yep, that worked out just fine. Going from here to here, switch this to an or, x in A and x not in B, x in A and x not in C. Yep, that's fine. And then or makes that a union. Whew. Hold it off. All right, there we go. Proved all those theorems. Next, we got relations. What's a relation? Going all the way back to discrete math, both of you know. A relation is just a set of ordered pairs. Yep, if I do A and SpongeBob together with 1 and 2, together with 3 and 9, this is a fairly useless relation, but relation nonetheless. This is our set theoretical notion of relation. Give this thing a name like R. R is equal to our relation. What does it mean to say that A is related to B now? A related to, not B, but SpongeBob is logically equivalent. That notation now means that the order pair A comma SpongeBob was in R. In general, X is related to Y is logically equivalent to the order pair X comma Y is in R. And so now that's our set theoretical notion of a relation. We've talked about relations before as being predicates that take two terms. We've already been using that notation for relations. Now we have a set theoretical definition for a relation.
Remember off the top of your head what our definition for a relation was?
Prior to this, we were saying a relation is a predicate that takes two terms.
There was the
No, you were thinking of a functional relation, which was a relation that for every input, it had a unique output. In whatever words we used, I don't remember. But yeah, that was a functional relation, so that was basically defining a function. Which, when we define a function, is going to be a special type of relation. It can be a relation where each left-hand element only shows up once. That'll be a function. Anyways, so a relation, set of ordered pairs. That's all a relation is from here on out. No longer have to think about two-place predicate. It's just a set of ordered pairs. All right. Now, let X and Y be sets. If R is a subset of X cross Y, then we say R is a relation from X to Y. We say X is related to Y, X related to Y, provided that X comma Y is in our relation R. I kind of already explained that over here. We say that R is a relation on X, provided that R is a subset of X cross X. Remember, our relations are sets of ordered pairs. So it makes perfect sense to talk about a relation as a subset of a cross product. Cross product gives us ordered pairs. The relation is going to be a subset of that. A relation is a set of ordered pairs. Okay, so let's do an example. Get used to some of our terminology here. If X is equal to set 1, 2, 3, and R is equal to a set of ordered pairs 1, 2, 1, 3, 2, 3, then this is saying that 1's related to 2, 1's related to 3, 2's related to 3. Notice X cross X would be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. It's all the sets of ordered pairs where our first element comes from that set and our second element comes from that set. So since R is a subset of X cross X, R is a relation on X. R only relates things in X to other things in X. If we did X is 1, 2, 3 and Y is 4, 5, 6, and we wrote out X cross Y, then that would have been 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 3, 3, 4, 3, 5. I think I said that weird. Shouldn't say this. That's going to be confusing without actually writing out the example. So here's an example of X being a relation, or of R being a relation on X. It relates everything in X, not everything in X. It relates things in X to other things in X. That would be pushing towards a functional definition. Correct. So let me do X cross Y example. I was just trying to say it out loud, but I don't want to make a mess of things. So let's do an example of that. We'll keep the set small. We'll say X is equal to the set AB. Y is equal to the set 1, 2, 3. And now R, if it is going to be a relation on X, or a relation from X to Y, then R is going to be a set of ordered pairs where all our left-hand elements come from X and all our right-hand elements come from Y. So I could take A and map it to 1. I could take A and map it to 3, and I could be done. There's one relation. Pretty useless relation, but relation. And it only takes things from X and pairs them with things from Y.
The relation has to have at least one element.
Now, here's another relation. Okay, this is a relation from x to y. But this is a relation. Everything in there is an ordered pair. I checked, I double checked. They're all ordered pairs. But really quick, let's write out x cross y. What would x cross y equal? A1, A2, A3, B1, B2, B3. So notice R here is a subset of this. So since R is a subset of x cross y, R is a relation from x to y. So that's what the first one was saying. If R is a subset of x cross y, then we say R is a relation from x to y. It only relates things in x to things in y. If I were to write out all the things are related, we have A's related to 1, and we have A's related to 3. We only related things from x to things in y. Any subset of x cross y would work. Notice that x cross y is a relation on x cross y. Could have let R be this whole thing. That's perfectly valid. So if R is a subset of x cross y, then we say R is a relation from x to y. We say x is related to y, provided that, or x related to y, provided that x comma y is in R. We say R is a relation on x, that's why I did in this example, provided R is a subset of x cross x. So in this example, R is a relation on the set x. In this example, R is a relation from x to y. Make sense there with the different terminologies? You're going to be saying a lot about relations. They never go away. Okay. Remember back to your discrete math days, something called an equivalence relation. Those are also stupid ubiquitous. All through math. Can come up over and over again. So our relation R on X, notice that our relation, we don't talk about being an equivalence relation unless it's a relation on some set. We never talk about a relation out in a vacuum being an equivalence relation. It's only a relation on a set that we talk about being an equivalence relation. So you might be tempted to say something like R equal to the set 1, 1, 1, 2, 2, 1, 2, 2. You might be tempted to say that this is an equivalence relation. Is it reflexive? Is it symmetric? Is it transitive? Yes, yes, and yes. Except for the first one, it's not reflexive. It's only reflexive if reflexive means for all x in x, comma, x is related to itself. For all x in some domain, x is related to itself. Because if our domain would have been the set 1, 2, 3, this is not reflexive on this set. It didn't relate 3 to 3. It's still symmetric, it's still transitive, but it's not symmetric. But let's go through all these because in theory, other people are going to eventually watch this. So let's go over what each of those are. So relation R on X is an equivalence relation, provided that for all A, B, and C in X, we first off have A is related to A. Everything's related to itself. We call that reflexive. And if A is related to B, then B is also related to A. We call it symmetric. And if A is related to B and B is related to C, then A is related to C. We call it transitive. And I think that, did these already come up when we were talking about set theory?
Equivalence relations? Or
These properties. We might have had these properties come up already.
Maybe not symmetric, but these types.
So now that we've said all of those, let's look back on R. Say that this is our R, and this is our X. Kind of writing all over the place. X is equal to that. We say that that R on X, this would not be an equivalence relation, although it is a relation on X. Notice that this R is a relation on X. It only relates elements in X to other elements in X, so it is a relation on X, but it's not reflexive. For it to be reflexive, for every element in here, that element would have to be related to itself. Or in other words, we'd have to have 1, 1 in here, 2, 2 in here, and 3, 3 in here. If we add 3, 3 to this relation, now it is reflexive.
But it's not.
Sure it is.
Oh, yeah, it is.
Now it becomes the equivalence relation. So it is reflexive now. We have 1 related to 1, 2 related to 2, 3 related to 3. Reflexive, got that. Now is it symmetric? What does symmetric mean? It means anytime we have 1 related to 2, we also have 2 related to 1. Anytime I have x related to y, I have y related to x. So anytime I find one tuple in there, I better find it, what would you call it? Its mirror image in there as well. Something. I wanted to say reciprocal at first, but that sounded weird. So if I have 1, 1 in there, I better also have 1, 1 in there. Oh, good, I do. If I have 1, 2 in there, I better also have 2, 1 in there. Okay, I do. If I have 2, 1 in there, I better have 1, 2 in there. Okay, I do. If I have 2, 2 in there, I better have 2, 2. If I have 3, 3, I better have 3, 3. Okay, we're good. Now, transitive means if I have x related to y and y related to z, then I better have x related to z. The way I kind of think about this is if I can take 2 ordered pairs and kind of force them to overlap, make a right-hand element cancel out with a left-hand element, the ordered pair I'm left with has to be there. So I can combine these 2 together, causing those 1s to cancel out. So 1, 1 and 1, 2, that would leave me with a 1, 2. Is that in there? Yes. I can combine these 2 together, 1, 2, and 2, 1. That would leave me with a 1, 1. Is that in there? Yes. I can combine these 2 together. The 2s would cancel out, and we'd be left with a 1, 2. Is that in there? Yes. So however we can combine 2 things together, it's still in there. That's how I personally think of transitive, but whatever you think of it is, whatever you think of it. All right, let's do some more, not so discrete, let's do some more high-level examples of equivalence relations. One of the most obvious equivalence relations is equals on the real numbers. Is every real number equal to itself? Yes. If A is equal to B, is it true that B is equal to A? Yes. If A is equal to B and B is equal to C, is it true that A is equal to C? Yes. So it's reflexive, it's symmetric, it's transitive, so equals is an equivalence relation on the real numbers.
Are we going through a lot of things about equivalence relations?
They're very useful. You might remember we use them for partitioning sets.
Yeah, it's fuzzy. I remember that they were important, but I also remember that.
Equivalence relations and partitioning of sets is one of those things that the first time a student goes over, it's a pain.
Yeah.
And the second time they go over, they wonder why they were ever confused the first time.
Yeah.
It's one of those things.
Partition analysis.
So we talk about equivalence classes. We talk about equivalence relations and equivalence classes. And that confusing the first time, and then after that, you just get it. And equivalence classes are going to be a useful concept in topology. Probably pretty soon. I don't know. I'm just turning through the book. I mean, I understand. I went through the book once and then again. And that's what I've done. No expert on the material. I did it once at college and then I went through it with you guys once. I've only gone through the book one more time than you guys. Or were you there for the first time? Okay. Anyways, far from an expert. Let's look at another example of an equivalence relation. Has the same mother, if we're talking about the set of all people, has the same mother is an equivalence relation. Do you have the same mother as you?
Yeah.
Yes, everyone has the same mother as themselves. So has the same mother is reflexive. If I have the same mother as you, do you have the same mother as me? Yeah. If I have the same mother as you, and you have the same mother as John Doe, do I have the same mother as John Doe? Yeah, so it's transitive. Or another one. Let's look at from geometry, congruence on triangles. Is every triangle congruent to itself? Yes. If triangle A is congruent to triangle B, is B congruent to A? Yes. If A is congruent to B and B is congruent to C, is A congruent to C? Yes. Let's try another one. Is the ancestor of on people? Let's see, is that an equivalence relation? Are you the ancestor of yourself?
What is that?
Now. And even if you want to say yes to that one, if I'm an ancestor of you, are you an ancestor of me? No. If I'm an ancestor of you, and you're an ancestor of Bob, am I an ancestor of Bob? Yes. So ancestry is transitive, but it's not reflexive, and it's not symmetric.
What about has instead of has the same ancestor rather than is?
Let's try one. So, has a common parent.
And we basically did that one, right? On same mother.
Let's just try it.
Okay.
Rather than has a common ancestor, we'll just go back one generation. So, if I have a common, do I have a common parent with myself? Yes. If I have a common parent with you, do you have a common parent with me? If you have a common parent with John Doe and John Doe has a common parent with me, do you have a common parent with me? No. So has a common parent is not. Has the same mother, yes. Has a common parent, no. And in case someone watching on lecture doesn't understand the has a common parent one, we could have Jack, Jill, and Bob. Jack and Jill can have child A. Bill and Bob can have child B. Bob and Jane can have child C. A has a common parent with B, B has a common parent with C, but A and C are completely unrelated. If A and C happen to be male and female, those two can get married and have their own kids. Really mess the family tree. But family tree where everyone get married is unrelated.
Same sister, but you're not or the same brother.
Yep. The brother of B can marry the sister of B and be completely unrelated. Okay. I don't know. Try another one. Love's on the set of all people. Does everyone love themselves? We'll assume, yeah. If person A loves person B, does person B love person A? No, definitely not. A lot of high school drama centers around that fact. People have been out of high school too long. And then transitive would be pretty messed up. Person A loves person B and person B loves person C. Does person A love person C?
If you never dealt with that, does that mean you didn't love anyone, or just everyone loved you?
Okay, good question. You just never know.
Okay. I think we got a good feel for equivalence relations. Hopefully that's enough examples to make it pretty clear. The author had one more example to check to see if this is an equivalence relation. So in his example, he says we're on R2. Oh, sorry, notation. So he says on R2, when we have R2 like that, that means R cross R. And if I were to write something like R3, that would be the same thing as R cross R cross R. So I'm gonna define a relation on R2. I haven't shown you the relation yet. Just define that notation for you. So R2, so we talk about the Cartesian plane, right? On R2, comma, define. So since it's on R2, remember, R2 is sets of ordered pairs, so I'm relating ordered pairs to other ordered pairs. So a relation on R2 is going to look like going to be an ordered pair of ordered pairs. That is in R2, that is in R2. Oops, missing parentheses here. No, not a conic section.
That essentially relation
No. Saying like a parabola?
multiple like a hyperbola.
No, that's just, I mean, you have two outputs for one input, but
Yeah,
if,
but not two. You have.
I don't know what you're thinking.
You have something like an ellipse or a circle where you have to have.
Where for one input, there's potentially two outputs.
Yeah.
Then if you were going to capture that graphically, that'd be a three-tuple.
It would. You don't have to.
Okay. So anyways, our relation has to look something like this. Or an ordered pair of ordered pairs. One thing in here has to come from that. One thing in here has to come from that. Relating elements of this to elements of this. What does an element of that look like? An ordered pair. Okay. So on R2, define x1, comma, y1 is related to our relation. He uses a tilde. Should I just use R though? We'll just stick with R for a second so that we don't. We'll use his notation. X1, Y1 is related to X2, comma, Y2, provided that X1 plus Y1 is equal to X2 plus Y2. I think that's how he did it. P1, P2 is related to Q1, Q2. Oh, sorry. Our two x's and our two y's. Used to writing x1, y1 for points on a plane. This is just better in keeping. Rather than, no, he even has a different. Because before we would have said something like x is related to y.
Right.
And now x just has two elements and y has two elements. So this is related to this if x1 plus x2 is equal to y1 plus y2. So we're creating a relation where the ordered pairs are related to each other if they sum to the same thing. So it has the same sum relation. We're representing it with this tilde. The question is this tilde equivalence relation? So first, let's see, is it reflexive? So I've got to see if the same thing is related to itself. So is it the case that x1, comma, x2 is always related to the exact same thing, x1, comma, x2? Yes, because it's always the case that x1 plus x2 is equal to x1 plus x2. So it's reflexive. Everything is always related to itself. All right. What about symmetric? If I know that x1, comma, x2 has the same sum as y1, comma, y2, do I then know that y1, comma, y2 has the same sum as x1, comma, x2? Yeah, symmetric. This is saying, if I know that x1 plus x2 is equal to y1 plus y2, do I then know that y1 plus y2 is equal to x1 plus x2? And the answer is obviously yes. And then transitivity says, if x is related to y, and y is related to z, does that give me that x is related to z?
Yes.
In that case, it's true as well. So yes, this relation is an equivalence relation on R2. Has the same sum. Then for have a note here, but I'm not sure what I was getting at. Problem with reading notes that you wrote years ago. So I think it's pointless. Okay. So I think we can call it there. And
How quickly are we putting in chapter 1?
pick it up with equivalence relations next time. Sorry, say that again.
When do we start chapter 1?
So we're almost done with relations. We just need to define equivalence classes. And then after that, we cover functions. And then we're on to topological spaces. So pretty much just missing functions. Functions is kind of a tough one. Functions are another one of those ones that the first time you come across it, you just struggle with it. So yeah, I'm guessing we'll have 2 classes on functions. Yeah. Anyways.
Yeah, a bunch of years.